A few lessons ago, when we looked at the equation of a straight line, y equals mx plus c, we learnt this formula for m, the gradient of the line. Change in y over change in x from 2 points on the line. So for example, we could find the gradient of the line joining these points here, 1, 1 and 3, 7, by applying the formula. If we call this point x1, y1 and this point x2, y2, we can simply apply the formula 7 minus 1 for the y values over 3 minus 1 for the x values and get the value of m, the gradient, as 3. Looking at this graphically, we can see there's our difference of 6 in y, there's our difference of 2 in x. So in other words, the gradient of a straight line is given by the difference in the y values over the difference in the x value. We're going to use this same idea to get the gradient at a point on a curve. Looking at a point on a curve, it's the tangent at that point that we use to get the gradient at that point. You can see that if we put the tangent at different points on this curve, we would get different gradients. We'll take the gradient at the point 2, 4. Drawing a tangent then, and we can draw any triangle to this tangent. Change in y 12 over change in x 3. That gives us a value of m, a gradient of 4. So the gradient of this curve, y equals x squared, is 4 at the point 2, 4. As we said, as we move along the curve, the gradient changes. A few samples here, different gradients at different points. If we make a table of those gradients, we get this. And notice that if we look at the x value, the gradient is always twice the x value. So we haven't proved anything yet, but we've noticed that the gradient is twice the x value at a number of points on the curve y equals x squared. And as yet we found nothing to disprove that. We found no points where that isn't the case. So if we write it as dy dx equals 2x, we get our notation for differentiation, differential calculus. It's the difference in the y values over the difference in the x values. dy over dx. We tend to call this for short dy by dx. And we call the function given by the gradient function. So what about if we had y equals x cubed? We'd get a gradient function of 3x squared. Y equals x to the 4, the gradient function we get is 4x cubed. Maybe by now you've spotted a pattern. The basic rule for the gradient function of the form y equals x to the power of n is that dy by dx equals nx to the power of n minus 1. Power to the front and multiply. Subtract 1 from the power. We haven't proved anything, as we said earlier, but we can illustrate these other examples by sketching. For example, y equals x cubed. So we're putting in here our x values and then the value of the gradient at that point. Or what appear to be the y values, they're actually dy by dx values. So this is the gradient of y equals x cubed. And looks like that. And we have actually shown that it is this function here, as we suspected from earlier. We can also find gradients of functions like y equals x and y equals 1. But they're straight lines, and we actually know what the gradients of these lines are. Y equals 1 is a horizontal straight line with no gradient at all. Y equals x will just have a gradient of 1. For every 1 that x goes up, y will go up 1 as well. Like so. So, to summarise our gradient functions. Have a quick go at these. I'll pop the answers up. If you pause the presentation now, try and answer the questions. I'll pop the answers up in a minute. Okay, here's the solutions. So for y equals x to the 4, dy by dx equals 4x to the 3. Again, power to the front and drop 1 from the power. We then put the x equals minus 1 in, and we get a value of minus 4. X to the 3 is minus 1. 4 times minus 1 is minus 4. Here, 3x squared. Put half in for x. X squared's a quarter. 3 times a quarter gives us 3/4.